Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will complete the discussion of step index fiber, modes of a step index optical fiber. We stopped at the right moment in the previous module where we had written down a matrix which connects the unknown coefficients A, B, C and D, and the coefficient matrix that multiplies this unknown vector A, B, C, D was actually the result of applying boundary conditions on the four horizontal components or the longitudinal components or the tangential components, and this is the equation that you had obtained. The right hand side of course is 0, okay. And if you look at the left hand side, please also remember that wherever I have mentioned only J nu, I actually mean J nu as J nu kappa A. Similarly, K nu will be K nu with a function of gamma A, okay. So, kappa and gamma, you have to be careful that kappa goes with J and gamma goes with K. That is just to simplify the notation, and once you have simplified the notation, this is the big matrix that you are going to get. And for this matrix or for this entire system of equations to actually have non-trivial solutions, it is necessary that the determinant of this matrix must be equal to 0. Okay. And when you write down the condition of determinant of this matrix to be equal to 0, you will end up with an equation which is shown in this blue line. Okay. You can derive this one. Okay. This is a small exercise for you to calculate the determinant and then show that this is the equation that you are going to get. It is a complicated expression or it is a complex looking expression, no doubt about it, but if you look carefully you will notice some kind of a structure. For example, the term that I have here in the first bracket, which I will call as term 1, okay. I will put a small circle around it just to show that this is not I, this is term 1, and the one that I have written here is term 2, okay. So, I have term 1 and term 2 here, and if we want I can write this 1 by gamma square plus 1 by kappa square as term 3, okay. So, I have these equations, and what you actually see from this one now is that if you look at term 1, you have the derivative of the Bessel function of order nu. So, therefore, you have J nu prime divided by kappa J nu, and similarly you have the derivative in the denominator, I mean in the cladding case, which is kappa nu prime divided by gamma kappa nu, and the term 2 that you have is essentially the same as term 1, except that J nu prime is getting multiplied by K0 square N1 square, whereas kappa nu prime term is getting multiplied by K0 square N2 square, okay. So, except for this multiplication, these two terms are essentially kind of similar to each other. On the right hand side, of course, what you have to essentially notice is that there is a nu in the denominator. In fact, there is a nu square in the denominator and beta is also present. Of course, what is the equation used for? This is the characteristic equation, okay. What is the characteristic equation? It is the equation whose solution is supposed to give you beta, but this is a very complex equation. The solutions are also not so simple. Even with good numerical methods, solving this complicated expression, especially for different orders and other things, and get the essential numerical accuracy is kind of difficult, not impossible, but it is difficult, okay. And this was very difficult in the 1960s, late 1960s, when these type of equations were first derived. Rather, they were derived in the early 60s, but their real use was in the late 60s. At that point, the computing power was not so high. So, solving these equations was not so easy at that time. Even now, solving these equations with the resulting numerical accuracies is kind of difficult, okay. But anyway, this is the equation that you need to solve if you want to find out the value of beta, and this is again much more than a transcendental equation, because beta is not just explicitly sitting here, but beta is also sitting in gamma square, it is also sitting in kappa square, and furthermore these kappa and gamma themselves are the arguments of the Bessel function. So, it is really complicated, is what I want to emphasize. There are a couple of additional relationships that you need to know, okay. So, you can see that C and D, which are the amplitudes of the electric field in the cladding, and D, which is the amplitude of the magnetic field in the cladding, are not really independent, but they can be related to the amplitudes in the core itself. So, A and B are the core electric and magnetic field amplitudes, and in terms of those you can write down the amplitudes of the electric and magnetic fields in the cladding. But there is a relationship between B and A which comes from third line or the fourth row of this matrix. So, you can either look at the third row, okay, which will give you some term times A, this term times B, some term times C, some term times D. The sum of all of that will be equal to 0, okay. But then you know that C and D themselves can be written in terms of A and B, and therefore you can actually obtain one set of equation which relates B to A, okay. Please remember, B is the amplitude of the magnetic field H Z, A is the amplitude of E Z, okay. Similarly, by following the fourth row of this matrix, it is possible for you to obtain another equation or another relationship between B and A, okay. So, in one equation you have the term 3 appearing is proportional to 3, but term 1 is actually appearing in the denominator because there is a -1, this term is actually raised to -1. In the second relationship, you have this term 3 appearing in the denominator, again because look at the sign here, it is -1, and then you have a term which is the term 2 appearing in, or it is appearing in the numerator term, okay. Now, let us look at some special cases. The general case of nu we will come to it, but let us look at a very special case of nu equal to 0. From our previous experience, we would hope or we would think that nu equal to 0 would correspond to certain modes which would essentially be fundamental. That is, these are the modes that will first start to propagate, but as we will see very shortly that this is not true. Nu equal to 0 does not give you the fundamental mode. What kind of modes do you get when nu equal to 0? Well, we go back to the characteristic equation and then we look at what happens when nu equal to 0. When nu is 0, the entire right hand side disappears, okay. Since the entire right side has disappeared, because I am assuming that this term 3 is not going to 0, okay, then I have either two choices, the first term going to 0 or the second term going to 0, okay. If I assume that the first term, that is j nu prime by kappa j nu plus k nu prime by gamma k nu is actually equal to 0, okay, then if I impose this condition back here in the relationship between B and A, I see that if this term is 0 in the relationship that I am showing here, okay. So, this is the term that is 0 and this term unfortunately occurs in the denominator, right. And because this is occurring in the denominator and nu equal to 0 is also occurring in the denominator, these two are essentially going to be something like 0 by 0 form, okay. But if in addition A happens to be equal to 0, then B will be finite for this one. So, what you will actually have is A equal to 0 from this relationship, and if term 2 goes to 0, then because nu appears in the denominator in the second relationship and this term 2 is appearing in the numerator, in this case it must be the value of B which must go to 0, okay. So, you can look at this particular thing, and then when nu equal to 0 you have, as I told you, one term, that is term 1 can be 0 or term 2 can be 0, okay. If term 1 is 0, then it also necessarily means that A equal to 0, okay, but A equal to 0 also means C equal to 0, but we remember that A and C are the amplitudes of E Z. So, what we have seen is that when nu equal to 0, E Z will be completely 0 if you assume first term to be 0, okay. E Z will be 0 both in core and cladding, in fact E Z will be entirely equal to 0, okay. Since E Z equal to 0, such modes are called as TE modes, okay, and the order of these TE modes always has to be 0, I mean that is the first order, the other order will come out, okay. So, you have TE 0 and M, I will shortly tell you what is M, okay. So, these modes are essentially called as TE 0 M modes, okay. Similarly, when term 2 equal to 0, this leads to the condition that B equals 0, which also means D is equal to 0, which further implies H Z equal to 0, and what you get are the transverse magnetic order 0 small m modes, okay. So, what you get are the TE and TM modes. Remember, during the start of this discussion we had said that there is no TE and TM mode in general for a step index fiber, and it is true. This is only for the special case where nu equal to 0 that you can divide the total solutions in terms of transverse electric and transverse magnetic. It would have been nice if these were to be the fundamental modes, but turns out that these are not the fundamental modes. Okay. So, what are the field components when you actually have TE modes, or rather how do I go about finding the propagation constant for TE 0M modes? So, how do I find the propagation constant? Well, the propagation constant comes from looking at I equal to 0, that is the first term equal to 0 as the eigen value expression or the characteristic expression. So, you have J0 prime divided by kappa J0 plus K0 prime. Okay. So, this is K0 prime divided by gamma K0. Okay. So, this will be equal to 0. The solutions actually can be mapped in terms of this type of an equation, where you will see that J0 prime by J0 can actually exhibit oscillatory behavior. In fact, it does exhibit an oscillatory behavior that goes something very similar to the tangential one. Okay. Similar but not the same as the tangential equation. The reason is J0 prime goes to 0 at some points, J0 goes to 0 at some points. So, it is actually switching between plus infinity and minus infinity. Okay. So, it does look very similar to the tan function, whereas K0 prime by gamma K0, K0 prime is the derivative of an exponential which would look like an exponential, especially because this K0 has to be applied away from the core, right. So, the 0 points are all excluded from the K equations, right. So, near 0 the K0 solutions are not going to be looked at because they are not part of the solutions anyway, because these K solutions are to be in the cladding itself. So, in that cladding K0 prime and K0 both look like exponential functions, and therefore, the ratios would only either decay or increase. In fact, that is precisely what happens. Okay. It would go something like this: wherever they intersect you will actually have a TE mode. So, for the same TE first order 0, okay, you will have multiple modes M, starting with M equals 1, 2, 3 and so on, and correspondingly you will have beta for TE 0M mode. Okay. So, what are the field components for TE mode? Well, for the transverse electric mode it is Hz, which must of course be some constant B which you do not know, but anyway. So, the field fundamental Hz field should be J0 kappa r. Okay. And is there any dependence on phi? Well, there is no dependence on phi. That is the beauty of having nu equal to 0, because nu equal to 0 implies e to the power j nu phi is equal to 1 with nu equal to 1, and therefore, these fields are independent of phi angle. Okay. Independent of phi means that they are azimuthally symmetric. So, you go around the fiber in a circular manner at a constant radius a, you will see that the field essentially looks like same. So, the magnitude of the field does not really change as you circle around the optical fiber. Okay. So, you have Hz, which is some J0 kappa r with respect to Z anyway, you know. This is in the core region, okay, and in the cladding region you will have some constant d, which of course can be rewritten in terms of constant b, but anyway I will put all of them into a constant b prime, and then I have K0, okay, gamma r. Okay. So, this is how the Hz field would look like. Ez of course will be 0. You can show that E phi will be equal to, which in this particular case will be j omega mu by kappa square del Hz by del r. Okay. This fellow will be equal to some constant. So, maybe that constant could be b or c double prime, something like that, but this is J0 prime of kappa r. Okay. This is in the core region, and in the cladding region they will be K0 prime. Okay. And then you can show that ER will be 0, similarly H phi will be 0 because r and phi are anyway related, and HR will also be like J0 prime. Okay. And it is this HR and E phi, so phi cross r, which would essentially go in the z direction, okay. Positive or negative z depends on the amplitude, actually it would be positive z only. So, this E phi cross HR will be the power, that is, or power density, which would be pointing in the z direction. So, in the nu equal to 0 case, okay, we have seen that the solutions can be divided into TE and TM, and in TE you can have solutions which are in TE modes you can have multiple solutions starting with say m equal to 1, m equal to 2 and so on. They all represent the different intersection points of the characteristic equation, okay, or the solutions of characteristic equation. So, you have multiple values of beta for the same nu equal to 0 value, and each of those propagation constants would be further included as the allowed mode of the waveguide. The similar ideas also are applicable for transverse magnetic mode, or they exist for transverse magnetic mode. There the eigenvalue equation will be different because the condition is that term 2 must be equal to 0. So, that n1 square and n2 square which go and multiply the individual terms of term 2 will actually push the TM modes to be slightly away from the cutoff for the TE modes. Okay. So, the TM modes would actually be very similar, but they would actually cut off at a slightly higher values of this one. Okay. So, they would actually slightly cut off at a higher values compared to TE modes. Okay. That is because of the n1 and n2 differences. If you were to sketch this TE mode field, okay, at least the electric fields if you were to sketch, you would find that the field is directed along phi. Phi means it is circling, right, and at r equal to 0 it would be like J0 prime, okay, and at r as it increases it would be a different thing. So, you will actually see that the H field lines would actually be like J0, yeah, the E field lines would actually be directed in this manner. So, these are the E field lines, okay, for TE01 mode, and these are the magnetic field lines that you are going to get, because magnetic field lines will be directed in Z as well as R direction. So, you have HR which goes as J0 prime kappa R, and this is how the field lines would actually look for magnetic field in the direction HR. I am plotting this one in the R phi plane. Okay. So, electric fields will be circling in. For the transverse magnetic fields, it is E phi which is equal to 0, E r which would be something like J0 prime kappa r of course, and then you have H z equal to 0 and you have H r equal to 0, but because E r is present there will be H phi. So, the field lines actually just change. So, what you would have called the field line for E in the TE case becomes the field line for the magnetic field in the TM case. Okay. So, these are the solutions which are very special solutions for the case of transverse electric and transverse magnetic modes, for the case where nu equal to 0. Okay. But in general when nu is not equal to 0, okay, you will have other solutions. Okay. And the solutions again can be classified into two groups. One is called as EH modes, okay, and the other is called as HE modes. HE stands for hybrid electric modes and EH stands for hybrid H modes. Okay. Meaning in the EH mode the magnitude of Hz will be greater than the magnitude of Ez, whereas in the hybrid electric modes the magnitude of Hz will be less than the magnitude of Ez fields. And since we know that Hz will have an amplitude B in the core, Ez has an amplitude of A, the relationships are essentially telling you that if the amplitude B is greater than A, then you get what are called as EH modes, and when B is less than A, you get what are called as hybrid electric modes. Sometimes these are called as E waves, and the corresponding hybrid H modes are called as H waves. Okay. It turns out that the fundamental mode is actually 1 when you set nu equal to 1. Okay. So, in that case you will have the first solution whose cutoff happens to be right at 0. Okay. We will talk about the cutoff conditions at least in the next class, but if you are not really happy about the cutoff condition, you already know that. So, you had J0 prime kappa A divided by kappa J0 kappa A being equal to, this is for the TE0M or TM0M modes. Okay. For TE0M modes the equation will be slightly different, but you might want to take this TM0M as an exercise. So, for TE0M modes this must be equal to K0 prime gamma A divided by gamma K0 gamma A, and we know that this TE0M mode will experience a cutoff when gamma goes to 0, right. So, when gamma is 0, you can see that this fellow here will actually be, so this gamma going to 0 means that this term here will be infinity on the right hand side, okay. And on the left hand side, what if you want to match the left and the right hand side, the only way to do that one would be to actually set this J0 kappa A equal to 0, okay. So, for the TE0M mode, the cutoff frequency is given by J0 kappa A equal to 0, and the first such solution happens when kappa A equals 2.405. This is the magic 2.405 value that we keep hearing in optical fibers. There is a general tendency to think that if V number is less than 2.405, the fiber is single moded, which is true, but where is that 2.405 coming from? It is coming from this cutoff condition, okay. Similarly, for TM modes, you can show that this is the same equation that is valid, okay, for the cutoff as well, for the cutoff of TM0M modes as well. So, the first mode will not appear until kappa A is exceeds or just equals 2.405, okay. It however turns out with a little bit of a lengthy explanation that HE11 mode, which is called as the fundamental mode in step index fibers, in general the optical fibers. So, this is the fundamental mode, simply because the cutoff condition turns out to be J1, okay, of kappa A equal to 0. Now, J1 is the Bessel function of the first kind and first order, which actually starts at 0, okay, goes something like this. So, because it is starting at 0 and this is completely allowed, you will actually have a cutoff frequency which is 0. So, cutoff frequency of HE11 mode is actually equal to 0, right. However, until V number becomes appreciably equal to 1, the corresponding propagation constant will not be that high. So, even though technically you could take DC signals and then just directly launch into an optical fiber by some method, okay, they would not propagate to a large distance because their propagation constant will be very small, okay. How does this HE11 mode look like? Well, the HE11 mode actually looks very interesting. At the center it is quite intense, but then the intensity kind of drops off as you go away from the center. So, if you were to plot the 2D plot for this one, so at the center it would be max and then it would go away like this on both sides, of course, right. This is the core, and when you hit the cladding they would actually continue and drop out or evanescently decay. So, inside this would actually go as J0 of kappa R, and that is precisely what was important about the HE11 mode, that its intensity is actually maximum at the center. You can actually express this J0 kappa R instead of a Bessel function. You can do a approximation in terms of Gaussian function, okay, with W called as the spot size of the fiber, okay. So, the field can be written instead of J0 kappa R, you can express them in terms of e power minus r square by W square, which is a Gaussian function. This is done purely to simplify calculations or to just get some number out of this one, okay. Working with Bessel functions is slightly difficult. So, if you approximate it with a nice Gaussian, then you can say W corresponds to the spot size, 2W then corresponds to the twice spot size, and the field would decay out by about 4 spot sizes, okay. And this spot size is important because if one fiber has an extremely large spot size and you then go with a fiber whose spot size is very small, when you try to couple them, right, the light is actually spread out much widely in this one because there is a larger spot size, whereas the light collecting capacity will be smaller for this fiber because it has a smaller spot size, and there will be a spot size mismatch, okay. Twice the value of spot size is what we call as mode field diameter, okay. And when you match two fibers, this mode field diameter must be matched as accurately as possible, otherwise you will actually have lot of problem, okay. Interestingly, this mode field diameter depends on the V number of the particular mode that is propagating. At least for the fundamental mode, the V number has to be very close to 2 in order to have well confined field, okay. If you look at how mode field diameter itself changes with respect to V for the fundamental mode, we will actually see that initially the confinement is very small and then the mode field diameter approaches the diameter of the fiber, okay. For larger values of V, that is close to 2, 2.2, 2.3, it would approach the value of A, but always being slightly larger than 2a. So, the mode field diameter is indicative of the amount of confinement of the field inside the core of the optical fiber, and this mode field diameter actually is very large, meaning very less confinement when V is very close to 0. So, this is another reason why you can't just take a direct DC signal and then launch it into an optical fiber. So, let me summarize. We started off with the step index profile, we followed the systematic procedure to analyze the modes and derive the expression of characteristic equation to obtain the values of beta, although that was a complex expression, okay, a complicated expression. Nevertheless, for the special case of nu equal to 0, we found that you can separate the modes into transverse electric and transverse magnetic. These transverse electric and transverse magnetic mostly look like circles intersected by radially outgoing lines. Depending on whether you are TE or TM modes, the circles will be either E phi or H phi, and in general for nu greater than this one, or nu greater than or nu arbitrary, the modes cannot be separated into TE and TM, but the modes become what is called as hybrid modes, and depending on whether Hz is larger than Ez or Hz is smaller than Ez, you have hybrid H modes and hybrid electric modes. The cutoff condition for TE and TM modes are the same, they have to be J0 kappa A equal to 0 is the characteristic equation. The solutions of those correspond to different modes, okay. Whereas HE11 cuts off at 0 and it has therefore the ability to be guided, technically guided at frequencies which are much less than the ones that are required for TE and TM, and therefore HE11 is the fundamental mode or the dominant mode of the fiber. In the next module, we will look at what is called as linearly polarized modes, which are the modes that are actually widely studied in literature because of the practical help that the fibers actually give you. We have assumed N1 to be greater than N2, but since the difference between N1 and N2 is so small, you can assume N1 to be approximately equal to N2, and when you do that, you will get the linearly polarized modes, which we are going to study in the next module. Thank you very much.